Welcome! In this explainer, we are going to pull back the curtain on the incredible, invisible forces that are constantly bending, stretching, and even breaking the rocks right under our feet.
I mean, really thought about it? It's way more than just a big squeeze. It's actually a pretty fascinating story of these massive forces locked in a constant, silent battle deep down inside the Earth.
Okay, so here's how we're going to tackle this. We'll start with the forces themselves, see how rocks actually react to them, figure out their breaking point, and then, the really cool part, look at how geologists can predict when it's all going to happen. This is the stuff you absolutely need to know for your geology courses and exams.
First things first, we've got to get a handle on the different ways a rock can feel pressure. Now, in geology, we have a specific word for this. We call it stress.
And this is a super important point. You know how if you're deep underwater, the pressure pushes on you from every direction equally? Well, stress in a rock isn't like that. It's a force that pushes or pulls in very specific directions.
So the first type is what we call compressive stress. Just think of it as a giant tectonic squeeze. This is the main force you find deep in the Earth's crust, where you have the crushing weight of all the rock above pushing everything together.
And next up, we have tensile stress. This is the total opposite. Instead of a squeeze, it's a stretch. It's a force that's trying to pull a rock apart, which happens in places where the crust is rifting.
And finally, we've got shear stress. The best way to picture this one? Imagine you have a deck of cards, and you push the top of the deck. See how the cards slide past each other? That's shear. It's a sliding force, and it's exactly the kind of stress you get along fault lines.
So you're squeezing, stretching, and sliding these rocks. What happens? Well, the rock actually changes its shape. And that reaction, that change in shape, has a name. It's called strain.
So here is the simple relationship you have to burn into your memory. Stress is the cause, strain is the effect. You apply a force, that's stress, and you get a deformation. That's strain. It's a fundamental concept in all of geology.
Okay, which brings us to the main event. When does all this squeezing and deforming finally cause a rock to just give up, to fracture and fail?
See, out in the real world, rocks are living a complicated life. They're not just getting squeezed or just getting sheared. They're experiencing this complex mix of forces all at once. So a rock's actual breaking point depends on that interplay between the normal stress, the squeeze, and the shear stress, the slide.
And this was a massive challenge for geologists and engineers for a long time. I mean, how could you possibly come up with a rule or some kind of tool that could predict the exact conditions that would make a rock break?
Well, luckily for us, some absolutely brilliant scientists cracked the code. They developed a way to precisely predict when any material, and that includes our rocks, is going to hit its limit.
And this is it. This is the secret code, known as the Mohr-Coulomb failure criterion. Now, don't let all the symbols scare you. It's actually pretty simple. It just says that the shear stress you need to break a rock, that's the tau, is equal to the rock's own internal stickiness, its cohesion, that's C, plus the friction you get from the normal stress, or the squeeze, that's the sigma part. So basically, a rock's strength comes from its own glue plus the friction from being squeezed. That's it.
An equation is fantastic, right? But for actually doing work, whether you're in the field or trying to solve a problem on an exam, you need to see it. You need a graphical tool to make sense of it all.
And here it is. The Mohr diagram is this absolutely genius tool that brings that equation to life. What we do is we plot the stress a rock is feeling as a circle. Then we draw a line that represents the rock's strength using our equation. Now here's the magic part. If that stress circle touches the failure line, snap, the rock breaks. This thing is a total game changer for geologists and engineers. And if you're taking any kind of geology exam, you have to know how this works.
All right, let's bring it all home and see how this stuff actually applies in the real world. And more importantly, how it applies to the kinds of questions you're going to see on your exams. So on the left, you see a classic exam problem. It's asking about the orientation of the biggest compressive stress, we call that sigma 1, for something called a normal fault. And that little diagram on the right? It gives us a perfect, simple way to see the answer. So here's the key takeaway. A normal fault happens where the crust is being stretched apart. When that happens, the biggest compressive force isn't coming from the sides. It's just the massive weight of all the rocks sitting on top of it. It's gravity, pulling everything straight down. So for a normal fault, sigma 1 is always vertical. Okay, let's lock this in. Quick recap. Number 1, stress is a force with a direction. Remember, squeeze, stretch, or slide.
2. Stress causes strain, which is just the rock deforming. 3. Rocks fail because of a mix of shear and normal stress, which we can beautifully visualize with a Mohr diagram. And 4. The direction of that biggest stress, sigma 1, tells you what kind of fault you're going to get.
So next time you're outside, look around. Every single mountain, every valley, even a tiny crack in the sidewalk, it's all telling a story about stress and strain. And it's a story that you can now start to read for yourself.